Okay, we're doing a resonance problem here from the book. So the question is about a flute playing near a string. So we want to know, why will the flute playing a 440 hertz sound with a 440 hertz fundamental, why will it make the string vibrate, knowing the length of the string and the wave speed? So we're talking about resonance here, which means that the driving frequency, that would be the flute driving and the string being driven. The driving frequency we have to have matching frequencies here. So we need to look at the driving frequencies being produced, and we need to look at the natural frequencies of the string at those lists if we're going to prove that this works. So we need to figure out those frequencies. So the flute, the fundamental looks like, it's kind of gross, looks like this. But there are other frequencies that the flute can produce, because it's, unlike a tuning fork, it's a little bit of a complex sound. It's not super complex, but definitely some overtones. All right, etc. So this one's 440 hertz. We can, try to find the length and find the wavelength of the next one and do all that, or we can just think about the pattern that we know exists. Because it has ends that are the same, the frequencies that it produces are all of the integer multiples of the fundamental. So, etc. So this is my list of driving frequencies, maybe, a few more. I don't want to go too far, it's not super complex. The question is, what are the natural frequencies of the string? Well, the string is constrained on both ends. Right, so it can produce that wave and this wave, right, and all that. But if we can figure out what the fundamental frequency is, we can just get those frequencies by looking at the multiples, because the ends are again the same. So if I look at the fundamental, I see that the length of the string is half a wavelength, and the length of the string is 25 centimeters. So the wavelength of the fundamental is 50 centimeters. And I know that v equals lambda f, so 660 meters per second that's 0.5 meters times f. So this tells me that my fundamental frequency is 1320 hertz. So this one's 1320 hertz. The next one is twice that, 2640 hertz. And then 3960 hertz, etc. Okay, again, we don't want to go too terribly far up, but look in the first 5 or 6 maybe. So the question is, are some of these driving frequencies matching the natural frequencies here? And yes, this one will excite the fundamental of the string. There will be some more up higher. 2640 will also be in this set, but it'll be a little too high for it to be feasible, but it'll definitely be in the set. So yes, there is resonance, because we have a match in those frequencies. A tuning fork, however, wouldn't do this, because a tuning fork, we would be driving with only the one frequency. So if it's a 440 hertz fork, we'd only be driving with 440 hertz, and that is not one of the natural frequencies over here. So that's why it wouldn't resonate, not a natural frequency of the string, and that's what we need.